like this, which is kept parallel to this uniform flow. Let the velocity be u naught. Draw this, everybody. So here is the leading edge of the plate, and this is the trailing edge of the plate. Okay. The distance from the leading edge and the trailing edge, BL. Hope you all noted this. Can we go ahead?
Yes, sir.
Okay. Now, when the fluid comes in contact with the solid surface of the plate, the adhesive nature of the fluid, because of its viscosity, okay, it starts to shear on the surface of the plate, and as we go perpendicular to the surface of the plate, the velocity will increase. On the surface of the plate, the velocity with respect to this stationary flat plate becomes zero. So this is an stationary flat plate. Okay. So what happens is there will be a growth in the boundary layer, and the boundary layer grows like this. Let me show you. So the boundary layer grows in this manner. Up to a distance, the boundary layer grows like that. Okay. So in this, if I draw a line perpendicular to the surface, the velocity profile will grow like this. Draw it, everybody. So this is the velocity profile, which encapsulates all this. Can we go ahead?
Yes, sir.
Okay. So if I draw a tangent here, like we did in our previous lecture, if I draw a tangent at this y equals to 0 for this profile, this becomes my tangent. Let's call this as θ1. Okay. And this becomes the, at this point, this becomes the thickness of the boundary layer. So this is a laminar boundary layer. So I'll write LB. Okay. Can we go ahead?
Yes, sir.
So you have the edge of the boundary layer. This is the edge of laminar boundary layer. Okay. It is the edge of the laminar boundary layer. Now, the lamin at this particular point, you will have the velocity, which will be 99% of the free stream value, 99% of u naught. So this is a laminar boundary layer, and in a laminar boundary layer, the if I take layers like this within the laminar boundary layer, let me draw this first here, then I'll bring it to that point. Don't draw this one. Let me finish this. You just imagine that. So these are like one layer adjacent to the other. Okay. Within this, what happens is the particles of the fluid will be exchanging. The particles will be going like this. So only between the adjacent layers, you will see the exchange of mass and momentum. Hope it is clear to everybody. You will not see the exchange from here to the bottom one. The exchange of mass and momentum is only between the adjacent layers. Suppose I shrink this. This is happening here. Okay, can I go ahead? Hope you understood this part. Thin layers I have taken.
Yes, sir.
And there is a exchange of mass and momentum within the boundary layer, between the adjacent layers. Can I go ahead now?
Yes, sir.
Okay. Fine. Let's go ahead. So these layers are like in a laminar, within the laminar boundary layer, the one layer is shearing over the other layer. So the structure is like well-defined structure and it is very fragile in nature. Okay. It's fragile means kind of delicate, you can say. So what happens is a small change in pressure gradient or heat transfer or due to the surface roughness or waviness, the boundary layer being structurally weak in nature at some particular Reynolds number, which happens at some distance x. Okay, let's say I'm measuring x in this direction. Fine. Let's say this is the direction in which this x is measured. So at some distance x from the leading edge, I will have Reynolds number, and Reynolds number is given by at any x rho u naught x by mu. So as x increases, the Reynolds number increases. So if the Reynolds number is increasing, if x is increasing, the Reynolds number is increasing. If the Reynolds number increases, it reaches a particular value at which the particles which were coming like this, okay, the particles which were coming like this will start to experience, will start to go in transition. So these particles will experience a transition like this. So instead of going in laminas, they will start to go in zigzag manner. Okay. So this region, small region in which they do so will finish here. After that, they become completely irregular. So this is a region in which the particles will become unstable. Okay. The structure which was stable and the fluid was flowing in laminas, it breaks completely and the structure becomes unstable and becomes completely irregular after the second black line. So this region in which this happens from here till here, this particular region is called as transition. So this is the transition zone. Okay. And before that, this entire region is a laminar region. Note that, everybody. Can I go ahead?
Yes, sir.
So after this, the boundary layer becomes further thick and it grows till the end like this. The boundary layer will further grow. And after this transition zone is finished, which finishes at roughly around when the REX value reaches 5.5 into 10 power 5. And this transition usually in open flows begins at REX equal to 3 into 10 power 5. So usually critical Reynolds number is taken as 3.5 into 10 power 5 in some case, or sometimes 5 into 10 power 5. Usually 3.5 for would be a good option. Okay. So between this Reynolds number range, it will be the fluid will be the external flow will be in transition. Okay. Then comes the flow after this transition zone is over, it becomes completely turbulent. So this region in which the flow becomes completely irregular is a region called as turbulent boundary layer. So this is the edge of turbulent boundary layer.
Yes, sir.
Okay. Now you draw one line perpendicular to the surface. So you cannot draw the straight lines like you made here for the velocity profile. In this, the paths are completely irregular and the particles will be experiencing the huge mass and molecular momentum transfer from one layer to the another layer. So, and the fluid particles move in packets. Okay, so this is like patches. So they will have irregular paths like this. The fluid particles would be going in this manner, completely irregular. And between the top layers to the bottom layers, they would come like this. Draw the irregular paths like that. Everybody do that. So this is the packets of fluid. They appear like patches. And the profile that you have here it was parabolic, and here it will be logarithmic. Fine. The velocity profile here is parabolic and here it is logarithmic. If I take a point here and if somebody is showing this velocity vector like this, do you know what is the meaning of this velocity vector? Deepali, are you there in class?
Yes, sir.
What is the meaning of this velocity vector that I am showing here in the turbulent boundary layer? If I show, it is called, right, this velocity vector is called as Reynolds average velocity. So it is the average velocity at that particular point which is gone in that direction. Okay. Then you draw a line which will be tangent to this particular surface, this velocity profile from this surface. Let's call this angle as theta. So we see that it has less slope, means this profile has less slope. What is the meaning of this? More velocity gradient or less velocity gradient?
Sir, more velocity.
Very good. So this will have more velocity. I'll write DL, gradient. More velocity gradient. Note that, everybody. So if we look at this from the top view, if we look at it, it will look like this. In the top view, the plate would look like this. Draw it, everybody. This is the top view of the plate, and this is the above one is the side view of the plate on which the boundary layer growth is shown. So if you observe in this region, the fluid was going with a similar pattern. Then that pattern in which the fluid was flowing breaks here like this. It becomes unstable pattern, not like the normal waves. It becomes like broken waves. Then it appears as packets of fluid like patches from top view also that are seen. And it will be going in, all particles will be going in a zigzag manner, that is irregular manner. Here B that is shown is the length width of the plate and L is the length of the plate. Right here, L as the length of the plate and B is the width of the plate. And X is the distance along the length of the plate from leading edge. It is X is always measured from the leading edge. Okay. Now I want to understand what happened here and here. Okay. In this, using this, we can investigate something at this particular points. Our points of interest now in discussion are these two dark blue dots. Okay. One point I took in the bottom of the laminar boundary layer velocity profile and the other I took on the turbulent boundary layer velocity profile. Okay. By Newton's law of viscosity, shear stress on wall, that is tau W, which is written as tau naught also, can be written as mu into dou U by dou Y at Y equals to 0. Okay. From above figure, we see that the velocity gradient dou U by dou Y at Y equals to 0 in turbulent boundary layer is greater than the velocity gradient, smaller the slope, larger the velocity gradient at Y equals to 0 in laminar boundary layer. Okay. So if I multiply mu on both sides, what do I get? Mu into dou U by dou Y at Y equals to 0 of in turbulent boundary layer should be greater than mu into dou U by dou Y at Y equals to 0 in the laminar boundary layer. So the shear stress in turbulent boundary layer will be greater than the shear stress in the laminar boundary layer. Bracket this thing. Hope it is clear, everybody. This is clear to everybody.
Yes, sir.
Okay. Now I'll ask you one simple question. Let's see how you answer this particular. Suppose I have a plate like this. On the surface of the plate, if I have 2 points, one is here, another point is here. This point 1 is located at a distance x1 and the point 2 is located at the distance x2. I'm just testing your knowledge. Don't worry about it, but you try to answer it. What can you say about the shear stress at 2 and shear stress at 1? Come on, guys. What can you say about the shear stress at 2 and 1? Let's say it is a GATE question and the GATE question model is like this. Consider the laminar boundary layer. Let's say this entire thing is your laminar boundary layer. Okay. Within that, so this is the edge of laminar boundary layer. If it is the edge of the laminar boundary layer and he is asking you this question, they will give you 4 options, let's say A, B, C, and D. Greater than, less than, equal to, not enough info. What would be your answer?
Equal, sir.
A. Why? What made you say that? Has the boundary layer become turbulent? That's why I asked you this question. Many people they think like turbulent is
Sir, I
coming
said
here.
that equal.
Huh? Sorry?
Equal, sir.
Why equal?
Equal. Because dou u by dou y same, sir.
It doesn't matter if the dou u by dou y. Do you think dou u by dou y will be same here and there? Everywhere. Huh? Do you think the velocity, if the velocity profile is here, is this? Do you think it will be the same all the time? Do you think the equation of this, and this curves, all three, do you think will be the same? Profiles may be the same, but the value of shear stress will change. Why? Because the slope will change. Dou u by dou y will change. The curves will start to change. If you remember the previous discussions, what happens is if you have a flow something like this, after some time this flow might become like this, or the flow might become something like this. Hope you understand. With time this would change. So let's say you don't know the answer of this, still the answer is pending. Okay, you don't have knowledge now to answer this particular thing. Just by looking at this, don't say tau2 will be greater because it is coming later. It would be different. Okay, we'll see. It might be the answer, but why we don't know. Okay, it could be the answer B, but it will never be this. It is not this. It could be either A or B. We'll see which one would be correct. You require more knowledge to understand and answer this question. Leave it. Hope you understand. For that, you need to learn boundary layer parameters. Right, boundary layer parameters. And you need to understand how to compute with respect to the profiles. In the boundary layer parameters, you write first one, boundary layer thickness.